In linear regression, it's common practice to distinguish between what we call as simple linear regression and multiple linear regression. The difference is not very great, but I will talk about the difference mainly because I want to explain some of the important concepts through simple linear regression, because simple linear regression deals with one predictor and one target, and we can visualize what's going on. Okay, so in simple linear regression, we use one attribute to predict another. So you've got one predictor, one target, and the equation, of course, now looks like this, right? You say y equals beta 0 plus beta 1 x. So y is your target, x is the predictor, and of course we wrote the form in which we include the error term or the residual term. Okay, so that's the target attribute, that's the predictor attribute, that's the error or the residual, and of course beta 0 and beta 1 are your regression coefficients, which the regression modeling tool will find for us. Okay, so let's take an example here. Let's say that we've got a data set regarding many homes, okay, and we know the number of rooms in each of those homes and we know the price. Obviously, this is a very simplistic model to predict the price of a home. We're not going to do that just by using the number of rooms. But I want to illustrate simple linear regression, and I want to use this example to motivate certain concepts. Okay, so let's pretend, just go with this simple example for the time being. Okay, so now I'm saying that we want to predict price in terms of the number of rooms. So I'm writing the regression equation as price equals beta 0 plus beta 1 times number of rooms plus the error term. Or alternately, I could have written price hat equals beta 0 plus beta 1 times number of rooms, right? Because once you put the hat here, you'll take out the error term. Okay, so let's say that our data looks like this. Simple data. So these are all the various houses we have. Okay, it may be tens of thousands of homes, but I'm just showing you 9 points here. That means we have data for 9 houses. For each house, we've got the room and the price. And the data looks like this, right? Of course, this generally satisfies our expectation that as the number of rooms increases, the price tends to go up. Okay, so but it's not going to be exact on a straight line. Okay, so what we are trying to do when we do regression, linear regression, is to find a line that closely goes through these points. Okay, and shortly we'll define what exactly do we mean by close, what is the best line, all of that. Okay, so we are trying to find a line that goes through the points. All right, so obviously we would not choose a line that's there, right, because that's not going through the points. We want a line that will approximate the trend that you see among the points. So we'll not choose a line here, right? We may not choose a line like that, even though it goes through the points, but we want the line to go through as many points as possible, as closely as possible. Okay, so that is the intuition that we want to clarify now. What exactly do we mean by a good line? Okay, so this is the prediction. And of course, it's a straight line because we are doing linear regression. We are creating a straight line. And if you extend the line so that it cuts the y-axis, okay, that is what beta 0 is. Okay, and that is why it is called as the intercept, because that is the place where it intersects the y-axis. Okay, so that's beta 0. And the slope of the line is what is beta 1. So in the case of simple linear regression, the coefficients beta 0 and beta 1 have this geometric interpretation. Okay, so slope is beta 1 and this is this. The intercept is beta 0. And of course, in this particular case, the slope represents essentially how much will the price change for 1 unit change in the number of rooms, right? So if the number of rooms increases by 1, by how much will the predicted price change? Predicted price, not the actual price. By how much will the predicted price change? It will change by beta 1 because the equation is this, right? You increase rooms by 1, then the total will change by beta 1 times rooms, beta 1 times 1, right? So that's the amount of change for a unit change in the predictor attribute. That's the interpretation. Okay, and going on further, of course, we already said that all the points are not going to fall exactly on the line. Some points may fall on the line. In this example, actually, none of the points is falling exactly on the line. these 2 points are very close, but they're not actually bang on the line. Okay, and therefore there is a difference between the actual value, which is the point, and the model value or the predicted value, which is the line. The line is the model, right? So if you want to calculate the prediction for a particular number of rooms, you will plug the number of rooms into that equation, which is the straight line, and whatever the line says, that's your prediction, right? So the predicted value is what the line is, but the actual value is here, and therefore for any given point, the vertical distance the point is away from the line is the error for that point. Okay, the epsilon for that particular point. Okay, so clearly we've got the error for each of the points, right? So you've got the error for that point, you've got the error for that point, you've got the error for this point, right? So for every point, similarly, you can compute it for all the points. You find out how far away from the line the point is, and that's the error for that particular point. Okay, so like this, you could find the error for every single point. Of course, what we are trying to do is to find the line for which this error is in some sense minimum. Okay, that is, you've got the error for every single point, right? So we can talk about the total error, and therefore the total error in some sense should be minimized, and that is what gives us the best line, because after all, you can draw many lines through these sets of points, right? You can draw a line like that, you can draw a line like this. In fact, you have an infinite number of lines. So now our task is to find the best line. Okay, and the best line is one which in some sense minimizes these errors for the point. Okay, so for example, this is what you have. You've got, again, this is just made up data. You've got the rooms, you've got the price, you've got the model predictions, and the actual prices, and therefore you can calculate the epsilon or the error, the difference between these two. Okay, so you can do that. So as I had pointed out, you can draw an infinite number of lines through these points. So the question is, which is our best line? Okay, so the best line is the one which I've already pointed out, which in some sense has this minimum error for every point. That is the difference between actual and the predicted values. Okay, and in fact, it's not just the minimum sum of the errors, it is the minimum of the sum of the squared errors, right? Remember, yi is the actual value, yi hat is the predicted value. So yi minus yi hat is the difference, but we square the difference and add up all of those. Remember, just like we did in the root mean squared error, right? As I said, statisticians always prefer to talk about squared errors. It has certain good properties. So that is why even here we are talking about the squared errors. So this is the sum of the squared errors. Okay, and we choose that line which minimizes the sum of the squared errors. So among all the infinite number of possible lines, there is one line for which this sum of squared errors is minimum, and that is what the linear regression finds. Okay, choose the line with the smallest value for this. Okay, of course you may say, well, since there are an infinite number of lines, how can you ever finish computing and finding the smallest value? Well, calculus allows us to do that without actually considering every single possibility, which we cannot because it's infinite. Right? We're not going to go into the details of how exactly that computation is done. Right? But all you need to do is to understand the fact that this is what is going on. We call this the least squares criterion. Okay, or sometimes the line that is fit, they call it the least squares line. So linear regression finds the best line, which is the least squares line. We will not get into the mathematics. Okay, let's just take a look at how the regression output looks like. And of course, you've done this in the first course. I just want to review it. So here you've got the Boston housing data, and you read the data, and here I'm building the linear regression model. And as you might recall, the function to do linear regression is called LM. And you indicate your dependent, the target attribute and the predictor attribute like this. Target attribute tilde predictor attribute, right? Of course, we are talking simple linear regression. So there's only one predictor attribute. And then you say data equals ph, which is the name of the data frame. Again, here I'm not showing you partitioning and all that. We'll get into all of that later. So here we are just building a regression model for a given data set. That's it. We're not doing partitioning right now. So once you do that, the model is stored in this variable called mod. And if you print out mod, it's going to show you this. Okay, it says this was the call that was made. This is the intercept. That is the coefficient for the room. In other words, this is beta 0. That's beta 1. And the regression equation, therefore, is the estimated median value for a household is minus 34.7. That is, beta 0 is minus 34.7 plus 9.1 times RM. Okay, so that's the regression equation. You can use this to predict the price for any house given the number of rooms. In this example, it's not a single house, it's a neighborhood, and it's the median value of homes in a neighborhood. So if a given neighborhood has a certain average number of rooms, you can predict what the median value for a house in that neighborhood would be using this. Okay, now there's one thing to note here. What if you've got a house which has got just a single room? Okay, in that case, if you apply this equation, the model will actually predict that the house is going to cost negative. Okay, clearly, homes don't have less than 4 or 5 rooms, and therefore those conditions would not arise at all. Just to clarify the connection between the regression output and the regression equation, that's what's going on, right? So beta 0 goes there, beta 1 goes here, and it's the same regression equation, beta 0 plus beta 1 times the predictor attribute. That's what this is.